Here are solutions to homework set number 7 for ECE 341. This homework set looks at uniform and exponential distributions. So suppose I've got two variables, a and b. A is the uniform distribution between 1 and 3. B is a random number between 1 and 4. What is the distribution of a plus b? Well, I could do that by using convolution by hand, using convolution in MATLAB, or multiplying Laplace transforms. So the first one's actually using Laplace transforms. Take the Laplace transform of A. This is a step, that's 1 over s, delayed by 1 second, delayed by 3 seconds. To make the area 1, this has to be 1/2 for the height. This has to be 1/3. So here's b, goes up at 1, goes down at 4. Total area is 1. In Laplace, I multiply the two moment-generating functions, the Laplace transforms. So there's a times b. Multiplying it all out, I get 1/6 s squared, e to the minus 2s, e to the minus 5s, e to the minus 3s, e to the minus 7s. Take the inverse Laplace transform. So this is pulling out the 1/6. This is a step, delayed by 2 seconds, a step, negative step, delayed by 4 seconds, a negative step, delayed by 5 seconds, a plus step, delayed by 7 seconds. So there's your answer. Another way to write it is for x less than 2, all the u's are turned off, so you're 0. At 2, this one turns on, so I get 1/6 times x minus 2. At between 2 and 4, these turn on, so this is 1 when t is bigger than 2 and less than 5. This gives you x minus x is 0. 2 minus 2 plus 4 is 2. 2 over 6. Between 4 and 5, this term turns on. So adding up all the x's, adding up all the constants. And finally, between 5 and 7, this term turns on. Add up all the x's, add up all the constants. And beyond 7, everybody turns on. In which case I get 0. Everybody cancels. That's one way to do it. A second way is convolution. This is actually a whole lot easier in MATLAB. So if I have x just going between 0 and 10, steps of 0.01, I added an epsilon just to avoid having to deal with greater than or equal to 0 or equal. It's never going to be equal. So a is a half for x between 1 and 3. B is a third for x between 1 and 4. Convolve a and b. Since this is continuous time I'm integrating, when I do that, MATLAB multiplies and sums. I need to multiply by dx. That's your integration step size. When I do that, the lengths will add, just truncating y to the same dimension as x, so I can plot x versus y. I got too many typos in here. Plot x versus y, I get this. So here's x, and there's y. There's the PDF. Which matches up with problem 1. Problem 3. If I have a op-amp circuit and the resistors have a 5% tolerance, what does y look like? Well, here I'm going to use a Monte Carlo simulation. What I can do with Monte Carlo is guess a random number for R1, that's 1k plus or minus 5%. Pick a random number for R2, 4k plus or minus 5%, and so on. Once I know the resistors, I know the inputs, calculate y. Repeat 1,000 times. Once I've got 1,000 y's, I can take the mean, standard deviation, and that kind of describes what the distribution is for y. To start out, I need to find out what's the relationship between y and the resistors. And there's a couple ways of doing that. One approach is I can write voltage nodes. I've got 1, 2, 3 unknown voltages, I need 3 equations for 3 unknowns. The first equation, for an op-amp with a negative feedback, V plus equals V minus. So let's do that, calling that X. I need 2 more equations. For the first one, at this point, current left plus current right equals 0. That's conservation of current. So that's X minus A over R1 plus X minus 0 over R2 equals 0. At this node, current left plus current right equals 0. X minus B over R3 plus X minus Y over R4 equals 0. 3 equations, 3 unknowns, solve. Well, I can do that clearing out the denominator, multiplying through by R1 times R2. Gives me this equation, multiplied by R3 times R4, this equation. Pull out the x's, now solve using Gauss elimination. I'm going to multiply the first equation times R3 plus R4, second equation by R1 plus R2, subtract, and the x's cancel. I get what's left over is minus R3, I subtracted, so plus R3 times R1 plus R2 times Y is equal to R2 times R3 plus R4 times A plus R4 times R1 plus R2 times B. Dividing, I get Y in terms of A and B, and some of these terms cancel. Like this actually cancels right here. So here's the equation for Y in terms of the resistors. Another way of doing that is use superposition. If A equals 0, solve for Y in terms of B. So if A is 0, this is 0, this is 0, that's an inverting amplifier. Y is minus R4 over R3 times B. Second, using superposition. If B is 0, I know Y in terms of this guy. That's a non-inverting amplifier. It's 1 plus the ratio. I know X in terms of A. It's R2 over R1 plus R2 times A by voltage division. So I get this for Y in terms of A. Add the two together by superposition, I get the same answer. So now that I know Y in terms of R1, R2, R3, R4, I can do Monte Carlo. With Monte Carlo, what I would do is guess a random number for R1, R2, R3, R4. This is plus minus 5% for 1K, 4K, 1K, 4K. There's A and B. Y, previous equation we had. Now repeat 1,000 times. When I'm done, find the mean, find the standard deviation. And when I ran it, that's what I got. Another way to describe it is to plot the CDF. If I take Y and sort it, and then take the order going from 0 to 1, this is the probability, this is Y, the voltage. The voltage goes between 3.7 volts and 4.3 volts with this PDF. So if I guess a probability like 0.7, that'll tell me what the voltage is. A question you might have is, okay, that's the CDF right here. What is the PDF? Well, the PDF is the derivative, which is not that easy to do. Or can I come up with a distribution that matches that CDF? We'll do that when we get to the Weibull distribution. That's in a couple days. So you're going to see this again. That's problem 3. Finally, problem 4. This is looking at a restaurant. Suppose I've got a restaurant. People arrive with an exponential distribution with a mean of 60 seconds. It takes 30 seconds on average to serve the customers with an exponential distribution. What's a 1 hour time slot going to look like? Well, what I can do is do a Monte Carlo simulation. So I've got the customers going from 1 through 13, and so on. Their arrival time. This is an exponential distribution. So this is the time customer number 1 arrives right here. That's the previous time plus an exponential distribution. To generate that number, I take a random number between 0 and 1. That's the function rand in Excel. Subtract 1 minus that random number, take the log, times 60 with a minus sign. That's an exponential distribution with a mean of 60 seconds. So that's when the second customer arrives, third, fourth, fifth. The time between customers is your exponential distribution. Ignore column C for now. The serving time is the same idea. The time it takes to serve is an exponential distribution with the mean of 30 seconds. So I've got these guys. The time that I'm done is the time that I place the order plus the time it takes to serve me. That's when I'm done. Going back to column C. What column C is, it's going to be the time that I arrived unless the previous customer is not done yet. And that shows up right here. I arrived at 2:22 seconds. The previous customer wasn't done until 2:28. So this guy right here is the maximum of the time that I arrive versus the time the previous customer is finished. So that's this guy right here. Fixing that column, I got the time that I actually got to the front of the line, placed my order, time it takes to fill the order, time that I leave. I can now calculate the wait time. The wait time is the difference in these two. That's how long I was standing in line waiting to place my order. And the worst case when I ran it was 36 seconds. The queue size, like right here, I arrived at 3:47 seconds. How many people were still at the store at 3:47.08 seconds? To do that, I go over here and see how many of these are greater than 3:47.08. And the answer is 2. And that can be calculated in Excel by saying, is this number bigger than the previous, 2 ago, 3 ago, 4 ago, 5 ago, and so on. This is a Boolean. Times 1 makes it a number, then the numbers I can add. So when you're done, you're left with a spreadsheet kind of showing this is what a 1 hour time slot looks like. This goes on for a while. And I can see what is the longest wait, what is the largest queue size. What restaurants do is they do studies like this. If the queue size is too long or the wait is too long, customers will leave. When customers leave, I lose money. So if this gets too long, I'll start hiring more cashiers, more people to take your order. If the queue size gets too long, again, I need more cashiers, more people to take your order. And what that does is that reduces the time to serve the customer. On the other hand, if this is too small, I have too many people taking orders, I could save money by letting some of them go home and reduce the number of servers. That increases this. And it's a constant game between the two. I want to keep the number of servers down, but I also want to keep the queue size down. Basically trying to keep the profits up. And all this is based upon the exponential distribution. That is problem number 4. So with that, that is homework set number 7 for 341.